Hey everyone, this module we're going to talk about natural climate change. We've been talking about some pretty big ideas so far, and really I feel like this is the part of class where we're kind of deep slogging through this doom and gloom of what are we supposed to do and climate change and how it's changing and how we're going to measure that. I wanted to kind of remind you that it's important for us to understand all of the science behind why the climate is changing, what sort of observations we can make, drivers, reasons. We're going to go through a lot of that stuff. Hopefully towards the end of the class we can kind of come back and say, like, wait, here are some things that we can really do, or what ways can we do to solve these problems. So one of the things that I've gotten as feedback from students is that it's really depressing. So just as a kind of keep after it sort of motivation, right? But one of the things that comes out of climate conversations often, whether or not people are really in tune with climate science, is this notion of, well, the climate of the Earth has changed, right? And that's what it does. That's what climate does. It changes, and that's absolutely true. So we're gonna in this module we're gonna talk about two or three. The third one's a little hard to kind of capture. Specific events or specific examples of really big climate change on Earth. But before we do that, in this video I wanted to talk about the things that affect climate from a natural point of view, right, outside of what we call anthropogenic or human-caused climate change, or how we change the physics and chemistry of planet Earth. So as we go through a couple of examples, I think we're going to talk about 6 different kind of things that can affect Earth's climate. And many of them are operating at different scales. The biggest one to think about are where these changes are happening, right? So we can have external variation. Those include things that happen outside of planet Earth, or in some cases to planet Earth itself, like how it's moving through space. Examples would be Milankovitch cycles, which we'll get to, the sun, right? What's going on with the sun? So those would be external variations. And then many of them are actually going to be internal variations. So things that happen to energy or change the rates at which heat energy is moving around Earth, the way that Earth absorbs or reflects heat energy. So that would be examples of internal versus external variation in climate drivers, right? Drivers for climate change. So one thing that can change climate, although again we're talking about a fairly large timescale here, is actually the sun itself. So this isn't an astronomy class, but fundamentally what happens inside of the sun is it's, first of all, it's really big, right? That's kind of how it works. And it's big enough that there's a lot of pressure inside of the sun, enough pressure that hydrogen atoms, individual atoms get pressed together with so much force that they fuse. They undergo what we call nuclear fusion. The nucleus of these hydrogen atoms, each with 1 proton and 1 neutron, asterisk if you're a chemistry expert, they then produce helium, plus some energy. Actually, a very small amount of mass is lost in that equation, and mass is related to energy by this funny little equation you've potentially seen at some point in your life. Energy is the change in mass multiplied by the square of the speed of light. Anyways, like I said, not an astronomy class, but the sun produces energy. And over time, it consumes more hydrogen and produces more helium. So what that generally means is that the sun is actually getting heavier over time. And if we think about the sun in its, 4.5, 4.6 billion year lifespan, it's actually increased brightness by about 30% solar output over that 5 billion year range of time. That's a big number, right? When we look at the sun and the energy given off by the sun, we call that the solar constant, right? The solar constant is kind of this amount of energy that we're always being bombarded by. When we look at how the energy from the sun changes with time, it is actually very well behaved. What we see are these peaks and valleys of periods where we have increased, periods where we have decreased. And you can see here as a graph kind of showing we've really been measuring the solar constant since the 1970s. We had the equipment to do that. But actually we can go back even further when we're looking at what's going on with the sun. So what we know is that when we look at those 11-year cycles, they actually correlate with periods of sunspots, right? So sunspots have to do with the kind of convection currents in the outer the outer shell of the sun. And we've been watching sunspots really since the 1600s, and what we see with sunspots is they as well have this kind of 11-year kind of increase, so increased number of observed sunspots, decreased. And those correlate very well with what we now measure as changes in the solar constant coming from the sun, these 11-year cycles. So we haven't seen significant changes in solar input to the Earth, especially things that are operating at the timescales that we're talking about in this class, right? So climate change really, within the last 100 years. And over that period of time, it's true the sun has increased over time, but not significantly in the last 100, 150 years. So when we're looking at short term, the sun is not a very good place to go for short-term climate change, but it can affect long-term climate change. The next thing that we're going to talk about is, again, an external change, right? Something that can change the amount of energy the Earth gets kind of by the way that the Earth moves in relationship to the sun, right? So I'm kind of thinking about spaceship Earth, right, and how it's moving with respect to the sun. So we're going to talk about Milankovitch cycles even more in this class, right? So you'll hopefully you'll have them all memorized. But really what we know is that in the 1920s really kind of figured this out, and like I said, there's some content later in the class to really go into the history of Milankovitch cycles. But what we know is that the way that the Earth moves around the sun changes over time, and it changes in this kind of periodicity, right? Meaning the first one that we'll talk about is the eccentricity of Earth's orbit. So thinking about how the Earth is rotating around the sun, this shape actually goes out of round and comes back into round, almost like a breathing pattern, right? So the eccentricity of Earth's orbit is always changing, but it's changing from one end member to the other. So looking at the eccentricity of Earth's orbit, it has about 100,000 year periodicity, meaning for it to deform and come back to its kind of original starting kind of shape of orbit takes about 100,000 years. So the next aspect that we kind of fall into the three primary Milankovitch cycles is this notion of obliquity. And that's essentially the rotational axis of Earth, which actually kind of moves back and forth over time. And there's about a 2-degree tilt in the way that happens. And that, again, thinking about how we have solar energy impacting Earth, we've got continents in different locations, that can affect, again, the amount of energy absorbed by the Earth in a given amount of time. So the obliquity of Earth has a periodicity of about 40,000 years. I'm just using some pretty coarse numbers. We're going to come back, like I said, with some more detail. And the last thing that we're going to talk about is the precession of, it's essentially the direction that the rotational axis of Earth is pointed. And this is nearly impossible to draw a picture of, but if we think about, here's the sun as my fist, and here's the Earth rotating, you can see my pen is oriented in the direction of Earth's tilt, right? It rotates around the sun or orbits the sun like this. That pen actually slowly also changes direction, but with a periodicity of about 20,000 years. The easiest way to explain this, to explain precession, is if you watch a top, right? If you spin a toy top, it's spinning very quickly, and the handle that you spun is essentially the axis, right? That's the rotational axis. And if you watch that top spin, the axis will actually slowly change orientation, but at a rate that's much different than the speed that the top itself is spinning at. So for our purposes here, we talked about the sun and we talked about Milankovitch cycles. Both of those are external variations, right? Again, the sun is kind of at very coarse timescales changes the amount of energy that we receive as a planet, and the way that the Earth is moving around the sun can also affect how that works. The interesting thing about these Milankovitch cycles is you kind of look at these three different aspects of how the Earth changes, and they make sine waves, right? So you could think about eccentricity as having a wave that has a 100,000 year periodicity, obliquity with a 40,000 year periodicity, and precession with a 20,000 year periodicity. And if you were to add all of those waves together, you'd get a really complicated shape, but occasionally the lows of all of those things would overlap, and we could get pretty extreme variations in climate that kind of work out through the interrelation between all three aspects of the Milankovitch cycle. And like I said, that's something that we're going to touch on quite a bit actually when we get into our climate modeling phase, right? Because this is something that really helped us kind of change the way we thought about energy meeting the Earth, right? We realized that it's not just constant over time. There had to be some change, and again, Milankovitch enters our picture there. Okay, so I'm going to stop the video here. We're going to start another video where we talk about internal variations and how the energy that the Earth absorbs can be changed by different things happening within the Earth. All right, I'll catch you then.